Alright, so we're moving on to our next form of energy. We've been doing kinetic energy, potential energy. We also looked at how energy was not conserved, but energy could be converted into different systems. And one of those that I mentioned was heat. So thermal energy, we're talking about heat, we're talking about temperature. Does anybody know the difference between temperature and heat? We can't measure heat. So heat is the term that we actually have for thermal energy. So this is the thermal energy in the system. We can't measure it though. So we can't stick a device into a material and say, well, this is going to have X amount of heat energy. Temperature, on the other hand, I'm pretty sure everybody knows that we can measure that. But temperature is a measure of how hot or cold an item is. Now, temperature is very useful mainly because if we observe a change in temperature, we could observe the change in thermal energy of a material. So that's what we use temperature for. But thermal energy can come in a couple of different situations. When we were looking before, we had potential and kinetic energy. There is potential and kinetic energy in terms of our thermal energy. So we have a kinetic energy side and a potential side. So we have a change in our kinetic when we have a change in temperature. So in kinetic energy, when we have a change in temperature, we have a movement, sometimes just a vibration, in the particles. When would you have a potential energy change for an object that absorbs heat? This is called latent heat. We give it a little symbol L, and we have two different ones for this. We have the vaporization and the latent heat of fusion. So vaporization turning into a gas, so therefore we are looking at a change in state. So if we're looking at a potential energy, we are looking at a state change. From a solid to a liquid, from a liquid to a gas. We would have the latent heat of fusion, so LF, when it is changing in between a solid and a liquid, or a liquid to a solid. And we would have the latent heat of vaporization when we're going from a liquid to a gas, or a gas to a liquid. Kinetic energy, we're talking about a change in temperature. It's the movements or the vibration of the particles. Our change in our thermal energy, delta Q, is going to be equal to mc delta T. So our change in temperature, which is our temperature final minus our temperature initial. We have the mass of the object in kilograms. We have our change in thermal energy, and that's in joules. Finally, we have C, which is our specific heat capacity. This is dependent on the material that you've actually got in there. So aluminium would have a different specific heat capacity to water, which would have a different specific heat capacity to air, which would have a different specific heat capacity to solid ice, which would have a different specific heat capacity to that of steam. All of these components in different states will have a different specific heat capacity. This one is measured in joules or kilojoules per kilogram. Now it's either degrees Celsius or Kelvin. So the scale of Kelvin and degrees Celsius are the same. So that means that if we have a temperature change of 1 degree Celsius, it would be the same as 1 degree change in Kelvin as well. The equation for latent heat. That one's quite nice and easy. Because it is not going with a change in temperature, it is only associated with a change in state. We have that our Q here is just equal to mL. So our mass times by our latent heat. Units for latent heat is joules per kilogram. There is no temperature change in this situation. So let's think about this when we actually go on and do it. So I'm going to go into the next slide. And what we're going to do is look at a graph. So here is my graph. On this side over here, I'm going to have time. And on this side, I'm going to have temperature. What I'm going to do is I'm going to draw a saucepan. So here is my saucepan. What I'm going to do, I'm going to put a large chunk of ice into my saucepan, like that. and then I'm going to put on the hot plate. Okay, so first of all, we're running this whole thing on the same hot plate. It's not going to be changing the hot plate up or down or anything like this. What's the first thing that's going to happen? So first of all, when we're looking at a solid structure, the molecules are going to be bound together, right? So in a solid, we're going to have our molecules as little circles. They're going to be joined together in some sort of pattern. This is probably not going to be the correct shape for water, but you can deal with it. So first of all, our solid in this situation, our ice is very cold, so therefore it's going to be at, let's say, -5 degrees Celsius. So when we start adding some heat in, initially, it's going to be down here. We're going to have some temperature there. What we're doing is adding energy to the solid molecule. That's going to make those little molecules, our little circles, vibrate along its structure. They're going to move around, they're going to jiggle, jiggle, jiggle. That's the best they can do in terms of having some kinetic movement inside of a physically bound structure. So that means that my temperature is going to increase. I'm going to have movement here with kinetic energy. I'm going to have some vibrations in my solid. After that, we get to what temperature for water when it converts from a solid to a liquid. It turns out 0 degrees Celsius. So we're going to have here at 0 degrees Celsius a change in state. So it's going to go from our solid to a liquid. And as you can see, it's in a saucepan. So therefore we have a container which to hold it in. But now my molecules, instead of being fixed in a solid, rigid shape, more freely able to move within that shape. So they are still held together. They have still got a barrier or a connection holding them all in location. But my cube of water will change into a puddle of water inside of my saucepan. But this is a change in potential energy. What we've done is we've separated that physical structure that is between holding it as a solid situation, and we've made it more fluid, surprisingly, into a liquid. Those molecules are able to move around each other. They're still held fairly close together, but the process of us melting the ice has no change in temperature. All of the energy is used to help move that rigid structure into a more fluid moving structure. No temperature change actually occurs there. I now keep the heat going. What's going to happen? It's going to eventually boil, right? So I now keep on adding some power to it. I'm going to increase the temperature until it hits still about 100 degrees. And then what happens? Our liquid turns into a gas. And what happens in that situation is our lovely little water molecules start to get out. They get out of our barrier or our container of liquid, and they become in a gas state. They're able to move around freely and travel around inside of the volume that is the room or a balloon or something like that. So it will fill up the space at which it can occupy. But that process again, converting between a liquid and a gas, is again another state change. So it has a constant temperature as well. If we could capture that gas and then heat it some more, we would be then able to increase its temperature. But that's generally actually fairly hard to do. So now we have our boiling water and we're ready to cook our instant noodles. So at the beginning, we have an MC delta T. We then have an MLF. We then have another MC delta T before an MLV, before finally another MC delta T. Are they the same C? So each one of these situations, we would have the C of ice, the C of water, and the C of steam. So each one of these specific heat capacities is going to be different. Which one is going to require more energy? The latent heat of fusion or the latent heat of vaporization? Moving from a solid to a liquid, you've just got to break only a very small little bit of a bond so that it will actually just collapse and become a liquid. They're still held together fairly well. But when you actually go and want to turn it into a gas, you've got to completely separate that molecule from the rest of the other particles altogether. You need to provide a lot of energy to make them move away from each other as much as possible. That's why the latent heat of vaporization is much, much larger than that of the latent heat of fusion. For ice, the latent heat of fusion is equal to 334 kilojoules per kilogram. The latent heat of vaporization for water is 2,260 kilojoules per kilogram. So significantly more. C of ice is equal to 2.1 kilojoules per kilogram Kelvin. C of water is 4.18 kilojoules per kilogram degree Celsius. Moving on from this situation, let's say while it's starting to boil, I turn off the hot plate, I grab a cube of ice, and I pop it in. How is heat being transferred in this situation? Which one has more energy? The hot one, right? So our boiling water, which is becoming steam, has a lot of thermal energy inside of it. The ice, though, does not have a huge amount of thermal energy. So therefore, the hot object gives its thermal energy to the cold object. Heat travels from hot to cold. The hot object will lose its thermal energy, giving it to the cold item. Questions for me? If there's no questions for me, then there are questions for you.